All right, let me go ahead and share the screen here. Okay, all right, well, good morning, everyone. So let's just start off with our usual announcements. Wednesday's lecture is on YouTube. I posted it kind of late. I didn't get it up until this morning, but it should be there now. So let me know if you have any trouble with that. Office hours at the usual time, usual place, 11 a.m. and then 4 p.m. And then the next homework assignment is due today. So after this, we're just going to have one more homework assignment and then we'll be done. So all I can say is just try your best to do the homework. If you don't have time, don't have the energy to do all of them, don't worry about it, don't stress. This is just supposed to supplement what we're doing in lecture, but please don't stress out about any of these. I'm being really laid back about turning in assignments. Okay, so I want to do a recap of some things, not just what we did on Wednesday, but some things that we did last week. And the goal for today is to kind of put together everything we've talked about in terms of these four different objects. We talked about affine varieties, quasi-affine varieties, projective varieties, quasi-projective varieties. And it may seem like that there's just a whole bunch of definitions all kind of floating around. But the goal for today is to put everything together and to say that really it's all the same definition. It just looks different, but everything really is the same. So with this in mind, let's maybe start with the definition of an affine variety and kind of remind ourselves what was happening there. So in everything we do today, I'm going to fix 3 bits of notation. One is when I say F, I mean an algebraically closed field. So think of maybe the complex numbers. When I say R, I mean a polynomial ring over F in n variables. And when I say S, I mean a polynomial ring over F in n+1 variables. And intuitively, the difference here is that I'm going to add x0 to the ring R, and then that's how I form S. Right, so we have these 3, F, R, and S. We're going to try to play off of these 3 today. So remember that an affine variety is a subset X of affine n space, which is irreducible and closed. But here I have to be a little bit careful that I mean the Zariski topology in affine n space. Right, so again, an affine variety means it's irreducible and closed. And here we just want 2 things. So number 1, we want this ideal, I of X, to be a prime ideal of R. And 2, we want X to be Zariski closed, meaning that X here is just equal to the 0 set of the ideal IX. Right, so putting those 2 is just what we mean to say that we have an affine variety. So once we have an affine variety, we can talk about the coordinate ring. So this just means you take the ring R and then just mod out by this prime ideal. So of course our coordinate ring is an integral domain. And we could also really abuse notation, and we could really say that our X is the same thing as spec of the coordinate ring. Right, so we can really just say that every point of X looks like a prime ideal. You know, the reality is we really want this to be M spec, the maximum ideals, but we'll just write this as the prime ideals because we're not really losing much by doing this. And finally, when we're dealing with affine varieties, we'll say that one is non-singular if the coordinate ring here now is Noetherian and integrally closed. So we're going to come back and talk about Noetherian today, but remember that there's different definitions of Noetherian. One of them is that if you have a chain of ideals that is ascending, that is, it's getting larger and larger, then at some point it has to terminate. So this kind of allows us to say this idea that there is the height of a prime ideal and things kind of don't go off to infinity. Okay, so this is the definitions associated to an affine variety. Finally, the dimension, of course, is just going to be the Krull dimension of the coordinate ring. So we can just define it in this way here. So this is now the dimension of our affine variety, the Krull dimension of the coordinate. Right, so now what about a quasi-affine variety? Well, it's simply a non-empty subset U, which is Zariski open in some affine variety X. And here, everything is still inside of the Zariski topology for affine n space. So another way to say this is that if we look at the complement So that is the set of points in X that are not in U, then it should be the zero set of some subset T satisfying this, right? T is contained in R, but T contains this prime ideal IX. Right? So this is what it means to be a quasi-affine variety. Just like before, we could abuse notation and we could say that our quasi-affine variety just looks like those prime ideals maybe that do not contain this coset here. Right, so this is another way we could write this by using this idea of spec. So again, it kind of looks like the set of prime ideals that do not contain this coset corresponding to T. Right, so this would be an equivalent way we could say it. And of course, we'll say that our quasi-affine variety is non-singular whenever the Zariski closure here is a non-singular affine variety. And then using that idea, we can define the dimension just to be the dimension of the Zariski closure, the dimension of this affine variety. Right? So this is what we mean by quasi-affine, just Zariski open in some affine. Now let's move over to projective space. And I want to define a projective variety. So this is a subset X, which is irreducible and Zariski closed. Right, notice that that's exactly what we said before. It's irreducible and closed. Now, of course, the difference is that we want to say in the Zariski topology for projective in space. But it's the same idea, irreducible and closed. So once we do this, of course, then we know that this means that our ideal here, IX, should be a prime ideal. But actually, we have to be a little bit careful. We actually want it to be a homogeneous prime ideal. Right, just to make sure that it's generated by homogeneous polynomials. But the second part is still the same. We want it to be Zariski closed. So X should equal to its Zariski closure, right? Just the set of points that vanish along the prime ideal IX. Right, so the only difference here now is that we want it to be a homogeneous ideal. So once we have this, then of course we can talk about the coordinate ring. In this case now we'll have the homogeneous coordinate ring. So it just means S mod the prime ideal. The reason why we're going to call this the homogeneous coordinate ring is that now we have a graded ring. So remember, this is the idea that we have to keep track of the homogeneous polynomials. Right? So here we know that our coordinate ring is a graded ring. And we can also define the dimension of our projective variety as just one less than the cruel dimension of our homogeneous coordinate ring. Right, so it almost looks like before, just now because we're working projectively, we want it to be one less than the cruel dimension. So that'll be our dimension here. And finally, we can talk about quasi-projective. So it's just like what you expect. It'll be a non-empty subset U that is Zariski open in some projective variety X. Right, so just like before, this has to be a Zariski open subset of another variety. And of course, what that means is when you take a look at the complement, then this should look like the zero set of some set T. But now I have to be a little bit careful that I want T itself to be homogeneous. So that's this weird condition here. So again, here I want T to be a homogeneous set. This last condition here just really kind of hits home the idea that I want it to be homogeneous. So I just want to make sure that everything kind of works out the way it should. Right. Sorry, to do that. So I accidentally clicked the wrong key. Okay. So once we have a quasi-projective variety, we can define its dimension, just like before, by taking first the Zariski closure. So this will be a projective variety. And then we can define the dimension, just like before, by looking at one less than the Kroll dimension of the homogeneous coordinate ring. Right? So same idea as before. Now, the last thing I want to mention is how do prime ideals relate to what we've done. So we see how we can talk about spec of O when it comes to affine varieties. And last time we mentioned what should happen for these projective varieties. So I want to remind you of the construction. Pick a point P that now has n plus 1 coefficients. But let's not let all of the coefficients be 0. So I'm going to stay away from the origin. That's what this says here. Then we can talk about the ideal MP. Right? We know that it's a maximal ideal of S. It's just generated by these polynomials, xk minus a sub k. But the problem is that this is not a homogeneous ideal because it is not generated by homogeneous polynomials. So you have to be a little bit careful. The maximal ideal of S is not quite what we want. So instead we do this trick. We look at the difference here of these polynomials. So here is xj minus aj, xi minus ai. We'll take this linear combination here. And now we have this polynomial that lies in the maximal ideal, and it is homogeneous of degree 1. Right, so we just kind of did this trick that we just wrote down something that's in the maximal ideal and it's homogeneous. And so now we have a prime ideal that is homogeneous. Right, so now everything does work out nicely. So I'm going to consider the ideal generated by these instead of the ideal here generated by xk minus ak. So we proved that this prime ideal is very special, that it does not contain the irrelevant ideal. Right, so the irrelevant ideal is just that ideal generated by these monomials x1 dot 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 xn x0. Right, so again, that's what's special about this. It does not contain this irrelevant ideal. So putting all of this together, if we have a projective variety x, then we can consider this map here, x going to spec x, that takes a point and writes down this homogeneous prime ideal. Right, so again, we don't really want to look at the maximal ideal MP. We want to look at this prime ideal because it'll be homogeneous. And so then this allows us to write the following notation. We can define proj to be the set of primes in spec of the homogeneous coordinate ring where those prime ideals are homogeneous and those prime ideals do not contain the irrelevant ideal. Right, so this would be the generalization for projective varieties. As you can probably see, it is a really weird kind of construction. It's not so clear why you would want to do this, which is why algebraic geometry can be kind of strange. So spec of O was already strange enough, but then when you go over here to proj of S, then it's certainly much stranger. Right? But I wanted to point out that the whole point here is that it comes down to this construction here. So you take a point, and you write down not MP, but proj of MP. Right? That's kind of what's happening here. Okay. All right. So now that we have these definitions in mind, let me quickly recap the last thing that we said on Wednesday. So this is where we were trying to figure out how affine varieties, in particular, the affine in space, is related to projective space. So we started off with this reminder of something that we've been doing throughout the entire course. We'll embed the affine plane into the projective plane by sending a point xy to this projective point x colon y colon 1. Right? And so once we have this, then we realize that the image actually looks like a quasi-projective variety, right? Because it is an open, Zariski open subset of our projective space P2. Right. So again, the image here is Zariski open, which really means that I can think of the affine plane as a quasi-projective variety. Right? That's pretty much what we've been doing here. Right? This whole embedding here, we can write in fancier language. just to say that it's really nothing more than saying the affine space, the affine plane, is a quasi-projective variety. Now, on Wednesday, we actually went a little bit further and we said, let's choose a linear polynomial. Let's call it f. Then the zero set of that polynomial is a projective variety. And moreover, if you look at the complement, then this here is an affine variety. Right? The complement is actually the same thing as affine in space. Right? That's what we worked out. So the complement is the same as affine in space. So this H here, we give a name, we call this a hyperplane. And when n is equal to 2, of course, we call this a line. So again, what this really shows is that affine in space is just a quasi-projective variety. Right? That's really what we worked out when we stated this proposition. So what I want to do today is convince you that there's really nothing special about an, that what I'm actually going to prove is that any quasi-affine variety is a quasi-projective variety. Right, so I'm going to write down a much more general theorem today. Okay, so let's set it up as follows. So again, to kind of recap where we were before, we know that if you fix a hyperplane, call it H for hyperplane, then there is an embedding that goes as follows. You take a point in affine in space and you send it to this projective point here. Right here, I've just kind of summarized the theorem and kind of the proofs that we worked out from before. But again, if you start with the point here in affine in space, you can send that to this projective point here. So as an example, say that we're dealing with the hyperplane at infinity. Right, so this will just correspond to this here. Then the map that we have actually is this map, which is just the generalization of what we had on the previous slide. This is what we're calling iota for embedding. So if you have an n tuple, you can send it here to a projective point by just setting the last coordinate equal to 1. Right, so again, what we have up here is just a generalization of the statement here. So we're going to use this idea now to generalize all of this for any quasi-affine variety. So the theorem that we're going to prove today is simply put this. Every quasi-affine variety is a quasi-projective variety. So philosophically, the way you want to think of this is we really didn't have to go through all of these definitions. So remember that we kind of started with things like affine in space, then affine varieties, then we went to projective in space and projective varieties. Then we talked about Zariski open sets, and then quasi-affine and quasi-projective. The whole point here is that really, we could have just defined a quasi-projective variety. And then as special cases, projective space, projective varieties, affine varieties, quasi-affine varieties, they're all special cases of a quasi-projective variety. So here, philosophically, the most general object you can study will be a quasi-projective variety. Okay. So I do want to go over the proof of this. And let me say that for the proof, we're going to do what's called a diagram chase. So what I'm going to do is actually stare at the following two diagrams very closely. So for example, over here on the left, we'll start with a quasi-affine variety U. We'll associate that with an affine variety X, and then we'll figure out how to embed that into a projective variety Y. So that once we have this, then all we have to do is just prove that U is the Zariski open complement of a projective variety Y. So that's going to be the idea over here on the left, how we're going to get all of this to work. Over here on the right, it'll be a bit trickier. So remember that if we have a affine variety X, we can associate that to a prime ideal IX that of course will sit inside of our polynomial ring R, and then we could look at the quotient and then talk about our coordinate ring OX. On the other hand, if I have now a projective variety Y, Then I have here a homogeneous prime ideal IY. That we know sits inside of our coordinate ring S, which of course is a graded ring. And then the quotient now should be our homogeneous coordinate ring SY, which again we know is a graded ring. So remember, I mentioned that there was this weird idea of duality that say if you have a map here perhaps of rings, so let's say perhaps going in this direction here, then for spec, that is really for the varieties, the arrow goes in the other direction. So whenever I have a map here that goes from the ring S to the ring R, I'm actually going to have an arrow reversing that goes from from X to Y. So we're going to place these arrows, we're going to play these arrows off each other. So if I have a direction over here for X going to Y, I'm going to use that to try to understand the map over here that maybe goes from IY to IX. All right, but this is going to be how we're all going to relate all of these things. Okay, so let's start with the proof. Well, U is a quasi-affine variety. So really what that means is I can take U and I can put it inside of some affine variety X. Right, that's just what it means to be quasi-affine, that it's like it's a Zariski open complement to some other affine variety. Well, X is an affine variety, so I can look at IX, this prime ideal, but now I know that my integral domain R is Noetherian, so the whole philosophy of Noetherian just says that everything should be finite. So this prime ideal IX is actually generated by a finite set of polynomials. Right, that's really what it means to be Noetherian. So this ideal IX is just generated by a finite set. Right, you actually don't really need that too much, but I want to point that out for the moment. So now what I'm going to do is I want to homogenize each polynomial in this ideal IX. And I'm not going to go over what homogenize means here on the slides. I do have it written up in the lecture notes. But remember that homogenize is just kind of our way of taking a polynomial and then writing it as a homogeneous polynomial. Right, so again, take our ideal sitting here inside of IX. There's only finitely many of them. So now let's homogenize them and make them here FK tilde. So in particular, if I look at the set T that contains all of these, this is a homogeneous set. Because I mean, literally it contains homogeneous polynomials. And that was one of the ideas of the homework assignment that's due today, is that a homogeneous set just means that it just contains homogeneous polynomials. So in particular, let's denote Y as this Zariski closed set. So remember that this is Zariski closed in the sense of what's happening with the Zariski topology on projective in space. Right, so again, here if I have a homogeneous set, then the zeros of that set are just by definition a Zariski closed set. So Y here is Zariski closed. Now, I need to explain how all of these are related. So let me define a new map, call it phi tilde, that I'm going to write as the composition here, where I know what phi is. Right, phi goes from U into X into affine in space. So now let's let I go from affine in space into projective space. And it'll do this exactly the way we said this earlier. All right, we'll just take our n tuple. We'll think of this as a projective point where the last coordinate I'll just set to be 1. All right, so this is our way of sending affine space into projective space. So really, to show that U is a quasi-projective variety, I actually have to show that IY is a prime ideal. That's really because what we've done here is that now I can think of U as sitting inside of projective space, really sitting inside of a projective variety, but I have to double check the Y is a projective variety. All that I know for the moment is that it's heuristically closed, but I don't yet know that it's irreducible. And that's the idea here. Right? So there's some things here that, of course, I'm kind of skimming through for the sake of time, but the point is that you really will sit inside of a projective variety once I can prove that IY is a prime ideal. Right? So that's really what I have to do now. I have to prove that this IY is prime. So again, let's try to ask, how are X and Y related? Right? So we have to be a little bit careful to stare at the relationship here. So I have a map, this iota, which goes from affine space to projective space by doing this here on the points. So let me ask, what does this do on the rings? So let's define I star as the pullback. And what that does is this: it takes maybe a homogeneous polynomial f tilde, and it returns a polynomial f by literally taking the last coordinate, x0, and just set it equal to 1. I mean, hopefully that makes sense, how this map here is related to this map here. Right, so again, the map on the rings literally says take a polynomial in n plus 1 variables, set the last variable equal to 1. So that is a polynomial in n variables. Right, that's really the same thing as if I have now an n tuple, I can think of this as a projective point where I'm going to set the last coordinate equal to 1. Right, so that hopefully it's clear that they're kind of one and the same, how this works. Now, this is what's happening with rings. So what's happening with the ideals? Now, this I star is a ring homomorphism, which means that if I take a look at the pullback of a prime ideal IX, then that better be another prime ideal. Right, remember, this is one of the homework assignments from earlier on in the course, that the pullback of a prime is a prime. So this here has to be a prime ideal, but also you can just work it out very explicitly that this ideal is generated in this way here. Right, so here I have the homogeneous polynomials that corresponded to IX. So literally you take the elements in IX, you homogenize them, that will be these here. But now I have this extra thing, x0 minus 1, but this kind of corresponds to all of these here, that I'm sort of setting the last coordinate equal to 1. Right, so again, this here is now a prime ideal. But sitting inside of this, I have IY, which is this ideal. Notice that IY has to be related to IX in this way, because notice how Y is generated. I mean, literally, Y is generated by homogenizing these polynomials. So the ideal generated by Y is literally the ideal generated by T. Right? That was the theorem that we proved earlier. So IY has to be this here by construction. So now IY is contained in this, but remember, I'm trying to prove that IY is a prime ideal. All that I know here is that the pre-image over here is prime, but now I have to wonder about over here. And actually it's not bad because they are very closely related. IY is a homogeneous ideal contained in this prime ideal. Now this should remind you of what we did earlier with this proj construction. Right, so maybe IY is not a maximal ideal, but I still want IY to be a homogeneous ideal. So the philosophy here is it should be the largest homogeneous ideal contained in this prime ideal. Right, so I actually wrote this here, right, that is maximal in this sense. So it's the largest homogeneous ideal contained in this prime ideal. Right, of course, the reason why we know that the pullback here is not prime is that it's generated by this polynomial x0 minus 1, which is not homogeneous. So these two over here are definitely not equal, but this is a prime. This here has to be maximal amongst those primes. So IY better be a prime. Right, if you want to, here's another explicit way you can write IY. So again, it looks like it's the largest homogeneous ideal sitting inside of this prime ideal, which is the pullback. Okay. So this actually means that, again, we know that Ix is a prime ideal. So according then to this formula, then we see that Iy must also be a prime ideal. Right? So again, I'm skimming over some details here because we don't really need to worry about them in so much detail, but this is what's happening. So again, if you start with the quasi-affine variety, you can always fit that into a quasi-projective variety. So what I want to do is spend the rest of the time going over some examples to try to hit this home. But first, any questions on how we went over the proof here?
Can you explain one more time how we know that this direct sum has to be prime?
So this here, you just have to kind of play around with it. It's going to go roughly something like this. One way to see this is you can say that this ideal should be maximal amongst all ideals homogeneous contained in this. And if it's maximal, then that kind of allows you to say that this here is going to be a prime ideal. That's kind of philosophically what's happening. The more rigorous way to say this would go something like this. Ix is prime, therefore the pullback here is prime. So now stare at this. So you can ask the question, take two homogeneous polynomials whose product is in Iy. Well, if they're homogeneous, then that means then they basically have to lie inside of one of these here, this I inverse Iy, but this here is prime. So then that means that at least one of those has to lie inside of this I inverse xy, but then that actually means that it lies inside of Iy. Right? That's probably the right way to say this, if you want to think of it this way here.
Okay, I think that makes sense.
Mm-hmm. Okay. All right, any other questions? Okay, right. As a caveat, if you actually do read this proof in an algebraic geometry book, it's done in a very different way typically. There's this idea that you can actually take any projective curve, you can cover it using affine curves. So that I kind of did this in a slightly different way to really hit home that really you're saying something about polynomial rings, you're getting this to work. But there is a fancier way to do this that doesn't use polynomial rings. It actually just uses the fact that you have an open cover by affine curves, affine varieties. Okay, so let's try to spend some time going over some examples now. Let's focus on the affine line, right? So just A1 of F, right? So let's just kind of keep everything very simple. Well, we know that there are only two affine varieties, at least two types. Either it's the entire line or it's just points, right? So actually very specific numbers, right? So little r here is just some number in the field F. So these are the only affine varieties in the affine line. So this was a homework problem. Similarly, the only quasi-affine varieties would either be the line minus a finite number of points. That number could be 0, but it's still minus a finite number of points. Or we just have just the singleton set here. These are the only quasi-affine varieties that we can have. So now I want to ask, by explicitly looking at these affine and quasi-affine varieties, why is it that I can think of these as quasi-projective varieties? So to do this, let's first fix an embedding of the affine line into the projective line. Right, so we'll just do this here. Right, so now I'm going to think of every affine number as a projective number. Okay. So let's observe that the affine line is quasi-projective because here I can take the entire line, projective line, and let's take away the point at infinity. So the way to read this is, remember that when x0 equals 0, then this kind of corresponds to the point 1 colon 0. So quite literally, I've taken the projective line and I've taken away the point 1 comma 0. Right? So again, when I write this here, x0, that should correspond to the point 1 colon 0. Right? So this is now why the affine line literally is a quasi-projective variety, because I took the projective line minus this Zariski closed set here. So A1 is Zariski open in P1. What if I just have one point? Right, so what if I just have this R here? Well, just like before, this here is a quasi-projective variety because I can look here at this Zariski closed set where Ix is now this prime ideal. So the way to think of this is if I set this here equal to 0, then this means I'm dealing with the point really R colon 1. But just to be a little bit precise, I have to be a little bit careful. Let's kind of take away the point at infinity, namely 1 colon 0, just to make sure things aren't a little bit crazy here. Right? So again, here I really have my ideal Ix, but now I'm just going to subtract this away just to make sure that things don't get a little bit screwed up. So now I can think of the one point as a Zariski open set. Right? Its complement is Zariski closed, which is the Z of T. Okay. So now what if I have the affine line minus a finite number of points? Right? So let's take a look at this here. So again, I want the affine line minus a finite number of points. Well, I definitely want to start with the projective line because that's kind of everything. But now I have to think, what does it mean to take away a finite number of points? So I could maybe take away the point 1 colon 0. That's what happens when I set x0 equal to 0. But then now let's take away these affine points here. So notice that this here corresponds to the point R1 colon 1. This here corresponds to the point R2 colon 1. And this here corresponds to the point Rn colon 1. So here I just have a homogeneous polynomial of degree n plus 1, but the zeros of this polynomial will correspond exactly to the points I'm trying to take away. Okay, all right, so any questions here? Okay, all right, so here's what's happening in this case. So let's keep going here. So now what we've actually just shown is that this affine variety and this affine variety quite literally are quasi-projective varieties because those are the first two cases. And then this last case here, this quasi-affine variety is quasi-projective because I just told you projective line, but now kind of do away with this homogeneous polynomial of degree n plus 1. Okay. Right, so this is why now these are all quasi-projective varieties. Now I just want to point out that you can do something slightly more general if you're dealing with affine in space. So this might explain a little bit kind of where some of these formulas here are coming from. So first of all, given an affine point, P, in affine space, AN, then I can think of this singleton set as the zero set of this maximal ideal. Right? So this kind of generalizes what we were doing a little bit earlier, say if I have like just one point here. Right? So again, I'll just think of now one point as being the zero set of this maximal ideal. Similarly, if I'm given a projective point, here now sitting inside of projective space, then we worked out last time that this projective point is the zero set of this homogeneous prime ideal? Right. So again, this P here, this point, is the zero set of this homogeneous prime ideal. Right. So this is kind of how we set everything up. The reason why we're even looking here at Proj MP. Now we have a slightly different, weird looking prime ideal, but we can still do this. So now we can try to put the two of these together. Let's take a look at our embedding iota, what we've been playing around with today, that takes an affine point P, and we'll think of this as a projective point by literally setting the last coordinate A0 equal to 1. Right, so we'll just do this. So now we can ask, well, what do we mean by looking at this affine point? So here, we'll just kind of look here at the zero set, but now we just have to be a little bit careful to make sure that the last coordinate doesn't equal 0. Right, that's kind of the philosophy here. I just want to make sure that the last coordinate doesn't equal 0. Okay, so any questions on how we did these examples here? Okay. All right. So I know that there's a few typos. I'll go ahead and clean this up. So let me just quickly tell you then, what is the plan for next week? So I'll admit I'm debating between one of two different things. So we'll just have the lecture on Monday, and then we'll have the lecture on Wednesday. So I'm wondering here if you can just tell me what you might prefer. You don't have to tell me today. You can maybe think about it and then tell me by email. Because we only have the 2 more lectures, I can either do 2 lectures on the Riemann-Roch theorem, and this would kind of explain what do we mean by the genus. We've introduced the genus before, but we haven't really said where the formulas are coming from. So I was hoping that we'd have like at least another week or so to kind of do things here in this class, and we'll just run out of time. But I definitely would like to say something about the genus if time permits. So Riemann-Roch theorem is one thing we could do. Another thing we could do is talk about sheaves. So one of the nice things about algebraic geometry is that you can really kind of view everything that we're doing here in a much higher level. And this is the idea of looking at sheaves. So I've kind of introduced the notation a little bit here to say that we do have sheaves a little bit, but I just haven't delved into them in detail. So I could spend a couple of days talking about what a sheaf is and then going over how that's related to everything here. So if you can, please tell me by email whether you prefer that we talk about the Riemann-Roch theorem for the last 2 lessons, or whether we talk about sheaves for the last 2 lessons. If you don't know what either one is, that's perfectly fine. But if you've heard about them and are maybe a little bit interested, then I can definitely go over either one of those on Monday and Wednesday. Okay, any questions, comments?
Yeah. I have a question. Do we
have sure.
final presentation?
Oh wait, I couldn't hear you, sorry.
Do we have final presentation?
Oh, no, we don't. I think I kind of mentioned this. It was in the video on Wednesday, but I forgot to mention this again today. No final presentations. I figured that everyone's already really stressed out. It's just too much work to get done. So I'm just going to do away with final presentations for the semester. All I'll say is just try to turn in your homework assignments. You know, if you're not able to do that, don't worry, don't stress. But no final presentations for the class.
Okay, thanks.
Mm-hmm. Okay, any other questions or comments?
Oh, might you talk about sheaves? Like, are you going to try to use category theory, or?
I will say a little bit about category theory. I'm not going to go into a whole lot of detail because unfortunately I really am only going to have 2 days to go over things. So what I'll do is probably talk about where structure sheaves are coming in, say a little bit about how this is related to commutative algebra, so we can actually talk about things like localizations and kind of why you would want to use localizations to talk about structure sheaves. And then from there, kind of introduce the general idea of what a sheaf is, and then just go over lots and lots of examples. So I definitely want to talk about like structure sheaves, tangent sheaves, probably a sheaf of differentials, and then end up saying a little bit about quasi-coherent sheaves and why those are related to things like Noetherian rings. Right. But a lot of that would be kind of introducing what the different sheaves are and how they're related to what we've talked about so far. Okay. Yep. Any other comments, questions? Right. Okay, well, if you have a preference, either way, send me an email. You know, if you don't have a preference, that's perfectly fine. I'll make up my mind. But I can do either one of those Monday and Wednesday next week. Either one will be fine. Right, well, you all have a good weekend then, and hopefully see you on Monday.
Have a good weekend.
Thank you. See you.
Right, see you then.